Let's recall the definition of definite integrals. To evaluate a definite integral using the definition, the first thing we do is to divide the interval from a to b into n subintervals using regular partition. Figure out the partition points and the width of the subintervals. And then you need to form what we call the Riemann sum. The definite integral of the function over the interval from a to b is defined as the limit of the Riemann sum as n approaches infinity. We have evaluated the definite integral of the function x squared from 0 to 1. We have seen the answer to the definite integral is 1/3. The definite integral from 0 to 1 of the function x squared equals 1/3. We have also seen the geometric meaning of the answer to the definite integral. We'll write the geometric meaning of the definite integral in words. Geometrically, the definite integral from 0 to 1 of x squared is the area under the graph of the function when x is from 0 to 1. We can just say from x value of 0 to x value of 1. We now talk about the geometric significance of the definite integral in general. In general, if the function is continuous, then geometrically, if the function is always non-negative, by that we mean if the graph of the function is always above the horizontal axis, then the definite integral of the function from a to b, it's not hard to imagine, is the area under the graph of the function from a to b. But what if the function is not always non-negative? Then the statement of the geometric significance of the definite integral is on the screen. We'll illustrate the meaning. Now let's say the graph of the function is something like this. The function is continuous on some closed interval from a to b. I'm not going to draw the vertical axis. So now let's say a is here and b is here. The function is continuous on the closed interval from a to b. So the graph of the function is something like this. In general, by continuity we mean the graph of the function has no breaks. Now let's draw two vertical lines. One vertical line is the vertical line passing through that point, the point on the x-axis with the x-coordinate of a, and the other vertical line is the vertical line passing through this point. This vertical line has the equation that x equals a. This vertical line has the equation that x equals b. In general, if the function is continuous, then the graph of the function and the two vertical lines, so together with the horizontal axis, enclose a plane region. Now let's use A1 to denote the area of the plane region above the horizontal axis, and use A2 to denote the area of the region below the horizontal axis. Then geometrically, the definite integral of the function f of x from a to b is a1 minus a2. That's why we say it's a net area. We'll use a particular question to illustrate the geometric significance of definite integrals. Now the solution. To do a question like that, we sketch the graph of the function y equals x. The integral is evaluated on the interval from -1 to 2. Now let's say -1 is here, and then 2 is here. The graph of the function y equals x is a straight line, something like this. This line has the equation y equals x. We also need two vertical lines. One vertical line is the vertical line with the equation of x equals -1. The other vertical line is the vertical line with the equation of x equals 2. Sorry, here's x equals -1. You see, the graph of the function and the horizontal line, together with two vertical lines, they enclose a plane region. And we use A1 to denote the area of the region above the horizontal axis. And we use A2 to denote the area of the region below the horizontal axis. That's the point of intersection of the graph of the function and this vertical line, x equals 2. So this point has x coordinate of 2 and the y coordinate of, you plug x value of 2 into the equation, you have y value of 2. And likewise, this point has x coordinate of -1 and the y coordinate of -1. Recall, the area of a triangle is computed using half of the base times height. To compute A1, the area of the region above the horizontal axis, we use the formula for computing the area of a triangle, half of the base. The base of the triangle is 2. And then times height. The height is also 2. So A1 is equal to 2. You can cancel 2 out from the numerator and the denominator. A1 is 2. And likewise, the area of the region below the horizontal axis. If you look at that triangle and treat this side as the base and this side as the height, it's an upside down triangle. So the area of A2 is equal to half of the base times height. Half of the base is 1. the base has the length of 1, and then the height is also 1. So this value is 1/2. According to the geometric significance of the definite integral, the definite integral of x from -1 to 2 equals the net area. By that we mean it's equal to a1 minus a2, which is 2 minus 1/2. This value is 3/2. We now talk about one of the most important human discoveries, the fundamental theorem of calculus, or FTC. FTC has two parts. Today, we concentrate only on how to use the second part. The second part of FTC gives us a very powerful tool for evaluating definite integrals. We'll use a particular question to illustrate how to use part 2 of FTC. Now the solution. So before using FTC, try to think in your mind, is the integrand continuous on the interval from 0 to 1? In this particular case, x squared is a power function which is continuous at all the real numbers. In particular, x squared is continuous on the interval from 0 to 1. So the condition of FTC is satisfied. You do not need to write the condition. To make the notations consistent, we are going to use f of x to denote the integrand. Let f of x be x squared. This is the formula for computing or evaluating the definite integral of a function from a to b. To use the formula, all we need is to get a particular antiderivative of the integrand, and then use the formula to evaluate the integral. And then we are going to use uppercase f of x to denote a particular antiderivative. You look at the basic integration formula, the power rule. A particular antiderivative of x squared is x cubed over 3, is a particular antiderivative of the integrand. Now we are ready to use the formula. So the definite integral of the function x squared from 0 to 1 is equal to, you look at the formula, the value of the antiderivative uppercase f at the upper limit of b, in this particular case the upper limit of 1, minus the value of the antiderivative at the lower limit of a, in this particular case at the lower limit of 0. So the definite integral is equal to the value of the antiderivative at the upper limit of 1 minus the value of the antiderivative at the lower limit of 0 equals antiderivative is here. You plug 1 into the antiderivative, you have 1 cubed over 3. Likewise, the value of the antiderivative at 0 is 0 cubed over 3. So the final answer is 1/3. You see, this method is much simpler than using the definition to evaluate the definite integral. Now let's recall, when using the definition to evaluate that simple integral, we need to divide the interval from 0 to 1 into n subintervals, and then we form the Riemann sum, and then we take the limit of the Riemann sum. The procedure was pretty long and tedious, but this is much simpler. Now, even better news. In the future, you can evaluate the definite integral of a function like that using only one line. I will show you how. The integral from 0 to 1 of x squared. In order to evaluate the definite integral, all we need is to find a particular antiderivative of the integrand, x squared. The antiderivative is x cubed over 3. You can use any particular antiderivative. And then we use a symbolic notation. This notation, we say we evaluate the antiderivative from 0 to 1. The meaning of the notation is the difference between the two values of the antiderivative, the value of the function at 1 and the value of the function at 0. So this symbolic notation means the value of the function at 1, the value of the antiderivative at 1, which is 1 cubed over 3, minus the value of the antiderivative at 0, 0 cubed over 3. So the final answer is 1/3. We now talk about some definitions and the properties of definite integrals. To simplify, we assume the function is continuous on the closed interval from a to b, and a is less than b. We look at this definition first. This definition says if the lower limit is the same as the upper limit in any integral, then the answer to the integral is defined as 0. Intuitively, this is simple to see. Now let's say if the function is positive, then the graph of the function is something like this. So geometrically, the definite integral of the function from a to a is the area under the graph of the function from a to a. When the lower limit is the same as the upper limit, the region is reduced to a line segment. Of course, the area of a line segment is 0. So that's how we see the definition. The other definition is that it's permissible for the lower limit to be greater than the upper limit. Now let's say if we are looking for the integral, let's say from 0 to 1, from 1 to 0 of x squared, in which you see the lower limit is greater than the upper limit. Then to get the value of the integral, all we need is to switch the lower limit and upper limit, let's say from 0 to 1, and then you add a negative sign before the integral. So the answer to the integral is negative 1/3. We have 4 other properties. This property can be proved easily using FTC. The next property says that if you have a constant factor in the integrand, then it's permissible to leave the constant factor out of the integration notation. This can be proved using the corresponding property for the indefinite integrals and the FTC. The next property says that if you have the integral of the sum or the difference of 2 functions, then it equals the sum of or the difference of 2 integrals. This can also be proved using the corresponding properties in the indefinite integrals and FTC. We'll only illustrate property number 5 using one special case. The special case that when A is less than B and C is in between A and B, also we assume the function is positive or non-negative. If you have a function that is non-negative and continuous on the interval from A to B, then the left-hand side, the definite integral of the function from A to B, geometrically is the area under the graph of the function from A to B. Now let's say this is the graph of the function y equals f of x. Now let's say C is a number in between A and B. C is somewhere in here. The first term on the right hand side geometrically is the area under the graph of the function from A to C. The area of the shaded region. And the second term geometrically is the area under the graph of the function from C to B. The second term is the area of that shaded region. That's how we understand property number 5. We now evaluate some more definite integrals using FTC. For this integral, we get a particular antiderivative of the integrand, which is negative cos of x, and then we evaluate the antiderivative from 0 to half pi. This equals the value of the antiderivative at half pi minus the value of the antiderivative at 0, negative cos of 0, which is cos of half pi is 0, cos of 0 is 1. The first term is 0 minus the second term is, you have negative 1. So the final answer is 1. Now let's take a look at the geometric meaning of the definite integral. Recall the graph of sin of x on the interval from 0 to half pi. The graph of sin of x is something like this. So now let's say half pi is here, pi is here, now let's say 1 is here, negative 1 is here. The graph of sin of x is something like this. illustration early. Now recall the geometric meaning of the definite integral. It's the area under the graph of the function from 0 to half pi. 0 is here. So you can see it's the area of the shaded region. Now we know that the area of that shaded region under the graph of the function sin of x from 0 to half pi, the area of the shaded region is equal to 1. Amazing. The integral on the screen is also straightforward. To evaluate the integral, all we need is to get a particular antiderivative of the integrand. Antiderivative of x to the power 4 is x to the power 5 over 5. And then plus 2 times a antiderivative of x cubed is x to the power 4 and then over 4. In this case, the antiderivative has two terms. In general, if the antiderivative is a little bit long, you can enclose the antiderivative in square brackets. And then you evaluate a particular antiderivative from 0 to 1. Plug 1 into the antiderivative, you have 1/5. And then plus 2 over 4, that is 1/2, minus the value of the antiderivative at 0 is equal to 0, of course. The answer to this is 7 over 10. We'll make some comments on two additional questions without getting the final answer. For this question, the integrand is essentially a polynomial of degree 2 or a quadratic function. If you multiply out the two factors, the integral is equal to the integral from 0 to 1. You multiply out the two factors, you have x squared, then plus x minus 2. Now you know how to proceed. For the integral on the screen, there's an absolute value of x involved. Now let's recall the absolute value of x equals x if x is non-negative, greater than or equal to 0. And the absolute value of x is equal to negative x if x is negative. So the technique involved in this question is to use one of the properties we mentioned to convert the integral as the sum of two integrals from -1 to 0. The same integrand, 5 minus the absolute value of x, and then plus from 0 to 1 the same integrand, let's say 5 minus the absolute value of x dx. At this point, we can use the property to get rid of the absolute value notation. The first integral is from -1 to 0. When evaluating that integral, x is treated as a number from -1 to 0. So absolute value of x is negative x. The integral is 5 minus absolute value of x is replaced with negative x. x, and then plus. In the second integral, x is treated as a number between 0 and 1. In particular, it's non-negative. That's why we can find minus, replace the absolute value of x with x. It's because when x is non-negative, the absolute value of x is the same as x. Right? We'll do one more step. Equals from -1 to 0. The integrand now is 5 plus x. And then plus from 0 to 1, 5 minus x. These two integrals are simple to evaluate. We'll stop here. Now we talk about the substitution rule for definite integrals. For the question on the screen, I switch the location of the two factors. After switching the two factors, then it's easier to see how to choose u. Now let's recall under what condition we can use the substitution rule. The integrand is the product of two functions, and then it is possible to choose u to be a function of x, so that one of the two factors will become a function of u with simple to compute antiderivative, and the other factor is the derivative of u times a constant. Now if we choose u to be x squared, the solution, we let u be x squared, and then we compute du, the differential of u. Du is the derivative of x squared, which is 2x, and then times dx. And then the other factor, so together with dx, now let's recall, we put the other factor, so together with dx in a box. It's an imaginary box, of course. Okay. After getting du, we identify the box from the differential. What we do next is to solve the equation for the box. So x times dx, whole thing in the box, equals 1/2 of du. You divide two sides of the equation by 1/2. Now our next job is to rewrite everything in terms of the new variable of u. But before that, you look at the lower limit and upper limit. In the integral, the lower limit is a value of x, and the upper limit is also a value of x. So to rewrite everything entirely in terms of u, we need to convert x value of 0 and x value of square root of half pi to u values, using the relation between u and x, so it is in the substitution, right? X value of 0 implies now we are getting the u value for x value of 0. 0 is the lower limit in the given integral. U value is x squared, which is 0 squared, so it is 0, right? And then x value of the upper limit, square root of half pi, corresponds to u value of u is x squared, square root of half pi, the whole thing squared. This is half pi. At this point, we are ready to convert the given integral entirely as a new integral of u. So the given integral, can I keep on writing from here? The given integral is lower limit corresponds to lower limit. That's the lower limit in the given integral. That's a x value. X value of 0 corresponds to a u value of 0. So that's u value of 0 corresponding to x value of 0. Lower limit corresponds to lower limit. And the x value of square root of half pi corresponds to u value of half pi. So u value is half pi. And then the first factor in the integrand is psi of u. And then the whole thing in the box is half of du. To evaluate the integral, you need a particular antiderivative of psi of u, which is negative cos of u. And you evaluate that you evaluate the antiderivative from 0 to half pi equals 1/2 negative cos of half pi minus negative cos of 0. Cos of 0 is equal to 1, and cos of half pi is equal to 0. So the final answer is half pi. You see, the only new additional step for the substitution rule for the definite integral is you need to get the u values for x value of the lower limit and the upper limit. Now let's work on one more question. Now the solution. We let u be 2x plus 1. Choose u so that one factor will become a function of u with simple to compute antiderivative. If you choose u to be 2x plus 1, then this factor will be, in terms of u, is u to the power of 100. It has simple to evaluate antiderivative. And then we compute du, the differential of u. Differentiate the function, you have 2 times dx. So dx equals half of du. We now get the u values for x value of 0 and x value of 1. X value of the lower limit of 0 corresponds to u value of 2 times 0. The relation between u and x is in the substitution. 2 times 0 and then plus 1, which is 1. And then x value of 1 corresponds to u value of 2 times 1 and then plus 1, which is 3. Now we are ready to convert the given integral entirely in terms of a new integral of u. So the given integral from 0 to 1, 2x plus 1 to the power of 100 equals when x value changes from 0 to 1, u values changes from 1 to 3. And then 2x plus 1 is u, so you have u to the power of 100. Also, you see dx is half of du. Write du here. You can leave out the constant factor of 1/2. Now we evaluate the integral of u to get the final answer. So you have 1/2. Antiderivative of u to the power of 100 is u to the power of 101 over 101. That is the antiderivative of u to the power of 100. We evaluate the antiderivative from 1 to 3. Now we are ready to get the final answer. It's 1/2 times the value of the antiderivative at 3 is 3 to the power of 101 over 101 minus the value of the antiderivative at 1 is 1 over 101. You can leave the answer in that form, but if you want to simplify, the final answer can be simplified as 202 and then 3 to the power of 101 minus 1. For the integral on the screen, we write the integrand in slightly different form so that we can see how to choose u properly. Now the integrand is the product of two functions. If we choose u to be natural log of t, then one factor will be a function of u squared, with simple to compute antiderivative. The other factor is exactly the derivative of u, which is the derivative of natural log of t. So we let u be natural log of t, and then we compute du, the differential of u, equals the derivative of natural log of t is 1 over t, and then times dt. We put the other factor, so together with dt as a whole, and then we identify the whole thing in the box from the differential. So 1 over t times dt, the whole thing in the box, equals du. Now in the given integral, this 1 and the lower limit of 1 and the upper limit of e are values of t. So we need to convert the t values of 1 and the e to the corresponding u values. So t value of 1 corresponds to u value of the relation between u and the t is in the substitution. U value is natural log of 1, which is 0, and then t value of e, the upper limit, corresponds to u value of natural log of e, so which is 1. At this point, we are ready to convert the given integral entirely in terms of the new variable u. When t changes from 1 to e, u changes from 0 to 1. So in the new integral, the lower limit is 0, and then the upper limit is 1. And then natural log of t, the whole thing squared, will be u squared. natural log of t is u. And then the whole thing in the box is just du. At this point, we just evaluate the integral of u. You must not go back to x. So antiderivative of u squared is u cubed over 3. And then we evaluate the antiderivative from 0 to 1. The value of the antiderivative at 1 is equal to 1/3. The value of the function at the value of the antiderivative at 0 is equal to 0. So the final answer is equal to 1/3. The question on the screen is designed for the physical meaning of definite integrals. In the question, you are given the velocity function of a moving object. You are looking for the displacement over some time interval, let's say from 1 to e in the question. Before we work on the question, now let's recall the physical meaning of definite integrals. If v of t is the velocity function of a moving object along a straight line, then the definite integral of the velocity function on the time interval from a to b, physically it means the displacement of the object over the time interval from a to b. Now let's work on the question. Now the solution. To get the displacement, all we need is to evaluate the velocity function. In this case, it's natural log of t over t on the time interval from 1 to e. We are going to rewrite the integral in slightly different form so that we can see the substitution we need to make from 1 to e, natural log of t, and then times 1 over t and dt. At this point, we can choose u. Now the integrand is the product of two functions, so choose u so that one of the two factors will become a function of u with simple to compute antiderivative. The other factor is the derivative of u times a constant. So we let u be natural log of t, and then we compute du, the differential of u. Du is exactly 1 over t and then times dt. Right? Now we treat 1 over t times dt as a whole, and then identify the whole thing in the differential. We want to write 1 over t times dt as a number times du. In this case, it's 1 over t times dt. It's just du. It's because we want to evaluate a definite integral. So it's the substitution rule for the definite integrals. Okay. At this point, we need to get the u values for t values of 1 and e, the lower limit and upper limit. Now, t value of 1 corresponds to u value of natural log of 1, which is 0. And the t value of e corresponds to u value of natural log of e, so which is 1. Now we are ready to convert the given integral of t entirely in terms of a new integral of u. When t changes from 1 to e, u changes from 0 to 1. So the integral of u is evaluated from 0 to 1. Natural log of t becomes u, and then the whole thing in the box, 1 over t times dt, becomes du. To evaluate the integral, we need a particular antiderivative of the integrand, so which is u squared over 2. And then we evaluate the antiderivative from 0 to 1. The value of the antiderivative at 1 is 1/2. The value of the antiderivative at 0 is equal to 0. So the final answer is 1/2. If the given velocity function is in meters per second, then the displacement should be in meters.